Okay, in this short video, I will try to explain our new approach to the fluctuation theory of Lévy processes using convex minorants. This is joint work with Jorge González Casares, who is currently finishing his PhD at Warwick. Okay, so X is a Lévy process, meaning that it's a continuous time process with stationary independent increments. Its trajectory will look something like this. It'll have some jumps. It'll possibly have infinitely many small jumps, microscopic jumps that you can't see in the picture, and may have a Gaussian component. Fluctuation theory is interested in the joint law of the time the infimum is reached, the position of the infimum, and the position of the process at the end of a given interval. Okay, so it's a classical problem studied over many decades, important in modeling. You want to know the joint law of such a structure. So our work is about sort of a new approach to this problem via convex minorant. So this red function here is a convex minorant of the trajectory of x. This means it's a pointwise largest convex function which is below the trajectory. And it's clear from this picture, indeed true, that convex minorant is going to be a piecewise linear convex function. Okay? So if I could characterize the law of the convex minorant, I would be doing well in terms of this triplet, because you see, so for example, the infimum of the trajectory over the interval 0 capital T would then just be, this is just linear bits. I look at all the linear bits, all the segments that have negative slope, and I just add up the vertical heights of that, and I get here. To get here, I just need to look at all the positive slopes. To get from here to here, I just need to look at the vertical heights of all the positive slope bits of the convex minorant. Okay, so convex minorant is a full function, maybe a tall order to characterize its law, but in fact, our paper shows that it's actually elementary. It requires very little in terms of the general theory of Lévy processes, or anything else, as you will see. So once we have this characterization, then fluctuation theory, so classical results of fluctuation theory, like minorant factorization, follow very easily. So I'll first show this second bit, and then I will discuss the characterization and the structure of its proof. Okay, so in order to derive the fluctuation theory, so the minorant factorization, say, for Lévy processes, I first need to state this simple consequence of the characterization of the convex minorant. Okay, so X is a Lévy process, and I take an independent stick-breaking process on 0t. T is a fixed time horizon. So what's a stick-breaking process, curly L? Well, I look at 0t, and I take a uniform point in 0t, and that's my first stick. I break this stick off, and then recursively I continue. I have a new interval, take a uniform point in this new interval, let's say here, that's my second stick, etc. You see, these sticks really converge to 0 geometrically fast. They're, of course, random. Okay, but they're independent of x. And then these sticks will have to do with the lengths of the faces of the horizontal lengths of the faces of the convex minorant. And so the infimum and the time it's reached and the final position, this triplet, has this sort of simple representation in terms of this infinite sum. Okay, so this is an equality in law. So what's on the right-hand side? Well, it's the stick-breaking process and independent draws from the law of x over stick-breaking lengths. Okay, so that's all there is. And the infimum, for example, is going to be just all the negative heights, right? The slopes will be xi n over ln, and the heights are just xi n. So all these negative heights I need to add up to get there. So this is a direct consequence. There is no coupling here. This is just an equality in law, coupling on this. On the right-hand side, you see, the right-hand side only depends on the law of x through its marginals. These are just independent draws of the marginals given the stick breaking, which is also independent of x. Okay, so it's directly proved from the characterization. Now, that's all good. But this equality in law actually contains the information required to derive most of the, if not all of the highlights of the fluctuation theory, as I will now show on the next slide. Okay, so the first thing to do is to rewrite this equality in law in theorem 1, so the right-hand side, that infinite sum. The fluctuation theory is about exponential time horizon. The previous theorem was on a fixed time horizon, but that matters not. I can take my exponential time interval, a random time interval exponential length, and I do my stick breaking, right? I condition this into stick breaking, and then this L theta, stick breaking on exponential time interval, it's an elementary fact that this stick breaking is a Poisson point process on positive reals, okay? And then, so that I just mark that Poisson point process, I decorate each point by a draw from the law of X. That's what I do. And by marking theorem, I get a new point process, okay? New point process. And the mean measure of this point process is precisely this. See, this is the mean measure of the point process L theta, and then I just have to multiply it with the law from which I'm drawing. See? So this is a picture of this psi, right? So you see here this x-axis here is the scale is logarithmic because these lengths become very, very small very quickly, and here it's not logarithmic. That's why these increments look very close to zero, because the times over which they're taken are very, very tiny, right? But those are independent draws, and then that's basically it. You see, because once I have this Poisson point process by theorem 1 from the previous page, I can write the infimum over the exponential time interval as the integral with respect to this random measure, right? So what do I need to do? I just need to add up I add up on this half, a quadrant really, right? So I add up all the negative slopes over all times. This is what this is doing. In order to get the other bit of the distance between the infimum and the final position, I have to add up everything on the positive side, right? All the points for all times, all the positive slopes, as the picture showed, right? So because this b minus and b plus are disjoint, that essentially is the Wiener-Hopf factorization, in the sense that this means that this guy and this guy, these vectors, are independent. And in order to understand the laws of the marginals of these vectors, of the components of the vectors, well, it's just Campbell's formula based on the mean measure of my Poisson point process, okay? So that's just that. So you see here, I've got the infimum, and all I need to do for the infimum is I've got to integrate it over the mean measure, the corresponding b plus or b minus, right? So that's it. And all the classical results follow in the same way. So I can get full Wiener-Hopf factorization, I get Rosin's criterion for the regularity, the starting point of the process, Spitzer's formulas for the expected supremum, etc. And also new fluctuation identities by simply decomposing the state space of the Poisson point process in pizza slices, say, something like that. Okay, so this is all in the paper. The paper is, by the way, quite short and contains a full account of these things. Okay, so now, also in the paper, the point of the paper is this SBRT, stick breaking representation theorem. Okay, so stick breaking representation theorem, on which the theorem we started with the consequence was based, is essentially, so it starts with X, looks at trajectory of X, looks at the convex minorant of X, and then asks the question, what's the law of that? And the law is given by a random piecewise linear convex function described by this formula here. Okay. So what is this formula saying? Well, it's saying that this infinite sum is really infinite sum over all intervals over which my convex function is going to be linear, and on each of those intervals, the slope on the nth interval, the slope will be ln psi n over ln. Ln is a stick breaking process independent of x, and psi n is again an increment of x over that stick. Okay. Now this n, the sampling, the indexing of n is not chronological, of course, but this formula still makes sense, and these terms are sort of active when time t is between an and an plus ln. Okay. This is just essentially taking these terms and ordering them according to slope. You see, according to slope we ordered. And this holds for any Lévy process. And not only does it hold for any Lévy process, this representation, but its proof is completely elementary, which was definitely a surprise to me. In other words, it doesn't require any of the Lévy theory. Okay, let me talk a little bit about the proof of this theorem. So the main thing in the theorem is to sort of notice that it connects two worlds. So world one is path of X and the convex minorant of X, and world two are these random piecewise linear convex functions. And it's difficult to work on both these things at the same time and mix them. What one should do is try to connect the worlds at the simplest possible level, and then just take the limits in different worlds, and that's how the proof actually works. So what's the simplest possible level? Well, say convex minorant of random walks that have densities. So the 3-2-1-4 transformation, which is this ingenious insight of Abramson and Pitman into the structure of a path of a random walk. So if a random walk says, for example, a density, the increments have density, then they give this guy is particularly simple and suffices to understand the proof of the piecewise linear convex function using discrete stick breaking. Okay. Now, then we take two limits. We take the limit in world one, and here the limit is simply that the random walk trajectory converges to the trajectory of the Lévy process, pointwise. So so you take a nested skeleton, say dyadic integers. Right? And all that matters here is not that this is a trajectory of a Lévy process, but this trajectory is uniquely determined by its values on the dense set, which it is because the path is Catalan. That's all that's needed here to see that these convex minorants are going to converge. Now, on the other side, these representations, this is essentially stick breaking representation, discrete stick breaking representation, piecewise linear convex function, and essentially our contribution to this is the limit on this side W2, in this world 2. Basically, it's possible to control this limit and show that you get in the limit this piecewise linear convex function in the theorem, in SBRT, by simply invoking only independent stationarity of the increments of X and elementary arguments, elementary geometric manipulations of piecewise linear convex functions and nothing else. Okay, so that's all in the paper, and the paper is, by the way, it's on the archive, and the proof is not complicated and completely elementary. Okay, so here we must mention the paper that in some sense started all this for us is Pitman and Uribe Bravo's paper that actually proves SBRT it proves our main theorem in the case of diffuse Lévy processes, but they they take the limit here in the middle, and that's very, very difficult, it turns out. They prove the convergence of the 3-2-1-4 transformation for Lévy processes. Okay, and that proof relies on a resulting fluctuation theory to do as Rogozin's result that states that a trajectory of a process that has infinite variation cannot stay in a cone, basically. Right? And so our approach doesn't require anything really of that complexity. In fact, our theorem implies Rogozin's theorem. Right? The SBRT implies Rogozin's theorem. Okay, so let me say one or two words about this 3-2-1-4 transformation of Abramson-Pitman. This is really a combinatorial observation so you take increments of a random walk, let's say a random walk with a density, and then you can do a path transformation, condition on these increments, and you can do a path transformation. Okay, you do a path transformation, and this path transformation consists of doing size bias sampling of the faces of the convex minorant. Okay, so you pick a face by some uniform random variable, you pick a face, and then you take it out of your convex function, and you stick this bit and this bit at the end. Right? You see, this is exactly what happens here. And then here you have the same problem as before. There's this recursive structure in the law of a random walk, it turns out. And not only, and then here the transformation does essentially a Vervat transform. of this excursion away from the convex minorant. So this is a bijection, it turns out. It is a bijection, and the fact that it is a bijection is crucial in determining the law of the convex minorant for a random walk. And Pitman and Uribe-Bravo approach to the proof of SBRT for Levy processes that are diffuse really consists of controlling these excursions away from the face. As in the so you look at the sequence of random walks converging, and then you need to control the excursions away from the convex, that face of the convex minorant, to the excursion of the away from the face of the Levy process. Okay, and that turns out to be a very difficult thing, particularly here at the ends, where you need to worry about whether there's a jump or not, and that's why they need this additional theory. Okay, while our approach is to really establish this and then look at the limits separately. So how do we do these limits separately? Well, the limit in this world one is very, very easy, because all you need to know is that you have this random walk, red random walk, and if it converges pointwise to a trajectory, then the corresponding convex minorants will also converge. See, it's clear. Now, the limit in world 2 is to do with convergence of piecewise linear convex functions. So the first observation is that if I give you a bunch of segments, out of those segments, whatever they are, whatever order I give them to you, you can always construct a unique piecewise linear convex function by simply ordering the segments according to their increasing slope. Okay, and now essentially our proof requires us to see that if we have such segments, and the segments, the lengths and angles, or the lengths and slopes converge, then the corresponding convex minorants will converge. Corresponding convex functions will converge. There are no minorants here anymore, right? That's the whole point. We don't look at the convex minorant in conjunction with the path. And that makes things much, much easier. It makes them elementary, in fact. You can see that this is going to happen, and that's exactly what our proof does. Okay, so that's it. Here are the papers of Abramson, Pitman, and Uribe-Bravo, and our paper is available in the archive. I hope this was helpful, really.